Okay, so today we have a new subject. It's related to the previous subject, okay, but we have a new ways for prove uh, the statements and the logical statement here. Before I start, I need from you to raise your hand. I want to know how many person around, how many student. Okay, okay, let's start. Okay, so uh, last time our subject was logical proposition. So first lecture we give introduction for propositional logic, and we take some logical proof or uh, what we called it logical equivalence rules to prove the logical equivalence. So then we take some law like De Morgan law, contrapositive, and so on. So we take the logical equivalence law and logical equivalence law related to the conditional statement or implication. Okay, and we take the proof of the equivalence and the proof of tautology also. We took this last time. Today, our subject, it's also related to the same subject. It's related, but we will take something new, which is mathematical proof. So we will speak today about logical inference and mathematical proof. We use actually logical inference and mathematical proof for same issue, which is mathematical proof. But logical inference, it's some rules that uh, formal, more formal than mathematical proof. More formal means it will take more steps to prove some statements. But mathematically proof, it's semi-formal. Yes, it's not really formal like logical inference rules. We did not take yet the logical inference rule. We will speak about it now. Okay, so what is the logical inference? Uh, when we have some assumption, some premises, okay, inference means get something from another thing. For example, if I give you some information and depending on this information, you get a conclusion. So we name this process inference. You get or drive or extract a conclusion, logical conclusion from some information, some premises, some assumption that given to you. That's how that's how the expert systems work. So it's logical inference. It's related to artificial intelligence and expert systems. It's work actually using this way of logical inference. And even the old, uh, not all, it's still usable in some projects, like programming languages that built for expert systems and for AI, like Lisp, for example, one of the expert system programming language to build expert system, they are using this logical inference rules or way. Okay, so what's the inference? Drives the conclusion, gets the conclusion from some premises. What's the meaning of premises? Some statement give to you, some assumption give to you that it's true. Okay, I give you some assumption. If today is rain and today is cloudy, if today is cloudy and today is windy, okay, I give you a premises, then you conclude that it will rain. Okay, so you derived or get or extract this conclusion from the premises that I gave to you. Okay, so we use it to solve some problems by logic. We usually, or we have to start from the premises to get to, or obtain the conclusion using inference rules. Okay, until now we get for the logic, we get the truth table, we get the logical equivalence rules. Now we have something called inference rule. We use it to prove a statement, logical statement, or to get conclusion from the premises. Premises, like for example here, just some examples for premises. Like if you have a current password, then you can log onto the network. This one premises, it's not enough alone. This another premises. You have a current password. So from these two premises, we can conclude. So the conclusion, you can log in or log into the network. So I said, if you have the current password, you can log into the network. And the other premises, yes, you have the current password. Then the conclusion, yes, you can log in the network or into the network. Okay, it's work like this. We have premises and we have conclusion from this premises. Sometimes it's not clear like this. We need to prove that our inference here is correct, or the law is the statements is correct. So we use something called inference rules. Generally, the inference rule, we get premises and another premises, and from it we get conclusion. How to write this statement? This means if we have a premises 1 and the premises 2, we can get That's why it's inference. This implication. We can get a Q. This the way of writing inference rule, and it's actually equivalent to this way. So this means P and P1 and P2 implies Q. This the premises, this the conclusion. This is a general form. It's not a rule. This one not a rule. This is a general form for inference rule. It's actually implication. And the inference rule is true. This means it's a tautology. This statement always true if the inference rule is true. So to prove an inference rule is true, we have to prove that it's a tautology. What's the meaning of a tautology? It's always true. Okay, let's take first inference rule. First implication, sometimes we called it implication rule. Why we called it implication rule? Because this one means implication. Yes, so it's always contain implication. So implication rule or inference rule, first inference rule, we have uh, modus ponens. It's not necessary to uh, use a long name. You can use MP, okay? The short name for the rule, MP, rule. So this modus ponens rule says if we have premises P and P implies a Q, then we can get a Q. How to write it as a rule? Write it as P, P, and P implies a Q. Okay, all this give us implies a Q. So simply you can memorize this like this way. Okay, P and P implies a Q. Okay, we have PP here. So from P we can get Q. So the result is Q. So if we have like this statement, we can get as a conclusion Q. This is the meaning. If we have P and we have P implies a Q, as a conclusion, we can get a Q. This one example. There is a storm. We can consider it as P. If there is a storm, it's P, the name of the premise. Okay, here. Okay. If there is a storm, if P, then the office is closed. Okay, this is Q. Okay, this means if I have this statement and this statement, of course you will know that the office is closed. If I told you that there is a storm today, if there is a storm, then the office is closed. What you will get from this rule? You will understand, you will inference that the office is closed. This is the conclusion, the inference. Okay, try to prove this rule at your home. How to prove it? You need to prove this. You need to prove that if P and P implies Q, this will give you Q implies Q. Another time, equivalence to true. Why? Because it's a tautology. You can prove this using truth table. You can prove this using the logical equivalence rule, okay? To get from this that it's always true, it's equivalent to true. Okay, so this first inference rule or implication rule. If I have P and I have P implies Q, then I can get or I can conclude a Q. Okay, another rule, empty or modest tenance rule. Empty rule says not the Q and P implies a Q, so not the Q with not the Q, then this will give me not P. So not the Q and P implies a Q give me as a conclusion not P. So if this one is true and this one is true, then I conclude that not P is true. This is the meaning of this rule, empty rule. We can prove this rule. For example, if you remember from the logical equivalence rule, P implies Q, it's equivalent to not Q implies not P. I can show you that we already took this rule here. Okay, this one. We have P implies Q. It's equivalent to not Q implies not P. So we can apply this here. So recall means remember that from the logical equivalence rule, not P implies Q, it's logically equivalent to not Q implies not P. Okay, so now here not the Q as it. Here from logical equivalence rule, we can write not Q implies not P because this one P implies Q, it's logically equivalent, so not Q implies not P. You can apply here which rule? This rule, MP rule. What MP rule? You see, if first side and first side implies this side, then that we conclude that this one true. So it doesn't matter not or something like this. Not the Q and not the Q implies not P. From MP, we can get this one. So not P is true. So by applying MP rule, we get not P. Okay, now return this statement as it. Return from, instead of this, get the original one. Then we get that not the Q, P implies a Q, it's actually give us not P. And that's what we need. So we prove that empty rule is correct. So if we replace again not the Q implies not P with the original value of it here, then we get that empty rule is correct. You can prove it again another way using the tautology and logical equivalent rule. You can use truth table also if you prove that this one tautology means always true, then also you can prove this empty rule. So shortly, what is the empty rule? Empty rule says not the Q and P implies Q give us not P. Give us not P. Okay. Here, example for logical inference rule and how to use it. So suppose we have P implies Q implies R. This we called it premises, yes. And another premises, Q and not R. Use inference rule, of course, to show not P. So what we need? We need to use these two premises to reach not P. How to use these two premises to reach not P? Using the logical inference rule. First of all, let's understand the example. We need not P. Where is P? Here. Yes. So first, to get this not P, okay, you can apply this rule. This is the only rule that give us not P. So not P have this one. Yes. With it. So if we get not the Q, this means not this one, then we can get not P. So look here. We have Q and not R. So it's better to return it to implication to get this Q and give us R. How? What's this? You remember the logical equivalence rule. We have some rule like this one. Actually, this one, it's equivalent to not the Q implies R. I can show you this rule. We already take it. That's why you have to make revision always. Look here. Not, let me make it bigger. Okay. Not P implies Q. It's logically equivalent to P implies not and not the Q. So if you have this one, you can get this one. And that what we applied here, we said we have this premises. From this premises, it's equivalent to not a Q implies R. Not the Q implies R from the logical equivalence rule. Okay, so now we have not the Q implies R, and we have this statement. From it, we can get not P directly. So this premises here, and this premises given to you here from logical equivalence rule for statement 2. Always you have to give numbers for the statements. when you use logical inference proof. Okay, so from statement 2 we get the logical equivalent for this one. It's not Q implies R. Okay, so we get to statement 3. We can apply empty rule, this rule, for statement 1 and statement 3. Put the statement 1 and the statement 3. Statement 3, it's not Q implies R. Statement 1, it's P implies Q implies R. So if we apply MT, see, doesn't matter what's this one. Consider it as K. Then this one K. So if we have like this, not K, P implies K. What we can get? We can get not P. From where? From this one, from MT rule. From MT rule, if we have not the Q and P implies Q, then we can get not P. So we have here, doesn't matter, X implies Y, implies Z, implies blah. It's not something, and same here, then we can get not P using empty rule. So apply empty rule to 3 and 1, we get not P. That's what we need. This is the question. Suppose you have 1, 2 premises. Use inference to show that not P means not P is correct. This means get not P from this premises. We get not P from the premises. So it's solved. Okay, we will take more examples, but we have to take more rules. A lot of rules, I know. It's mathematics, so you have to know all the rules. Okay, most rules, it's simple and easy. It's you have to memorize at least the short name, MP, MT, HS, DS, okay, to say which rule you applied here. This the tautology means if this inference rule correct, then this statement always true. Focus here. We need to focus here. Okay, focus here. How it's write it as implication. This line means implication. When you have premises like this means and. So as you can see, P and P implies Q. It implies this one, the conclusion Q. Okay. So focus here about the inference rule. First rule we give you MP. If P and P implies Q, okay, P and P implies Q, okay, together then we get the Q. Empty rule says if we have not the Q and P implies Q, so not the Q, Q here, then we get not P. Okay, HS rule says if P implies Q, Q implies R, then from P you go to Q, from Q you go to R, then you can go directly from P to R. So if we have P implies Q and we have Q implies R, we can conclude that P implies R. Okay, so this is the HS rule. TS rule says P or Q, this first premise given, and not P. P or Q and not P give us a Q. Okay, so if we have P or Q, P or Q with not P, this give us a Q. Addition rule. Addition rule says if I give you premise P, it's true, then you can add anything and it will be true. Okay, for example, if I said the sun, it's rays from the east. It's true. I give you a premise. If you said the sun, now you can add using or any other premise and the statement will say true. You can say it, okay, then I can say the sun come from, okay, come from the east and the sea, or not and, or the sea sweet water. Is it a true statement? Yes, it's true. Why it's true? Because first part, which is the sun come from the east, is true. So true or anything, it's true. So if I give you premise P, you can make or with any other premise and the statement or this conclusion will be true. So if this one true, the conclusion when we make or with any other statement, it will be true. Simplification. Simplification. If P and Q, of course, it gives us P as true. Because for this statement to be true, this means P true, Q true. Okay, so the rule said P and Q give us P. Also, P and Q give us Q also. So it can give us P, it can give us Q. This simplification rule. Okay, conjunction rule. If I give you premise P and premise Q, this means P and Q true. The sun come from the east, and I can give you another statement. For example, the sea is salty. So you can say the sun comes from the east and the sea is salty. You can connect using and. If the two premises true, then you can connect using and. Resolution rule. It says like this. If P or Q is a premises, P or Q, another premises, and not P or not P or R. Okay, look here, P and not P. Then this give us a Q or R. A Q or R. One of them must be true to make this true. So this is the meaning of this rule. So this resolution rule, if I give you P or Q and give you another statement, not P or R, you can set Q or R. You can use all this inference rule to prove the statements. We will take more examples, but first, let's take another term. Ahmad, it's better to turn off your mic. Okay, so valid argument. Okay, uh, let's speak about mathematical proof. Mathematical proof, it's contain hypothesis, a set of hypotheses given to you. You can consider it as true, or if you find that this hypothesis is true, then the conclusion Q is true. So mathematical proof, it's always like this. If the hypothesis or the premises given to you, if Q1, Q2, Q3, and Q until Qk, many premises given to you, if they are true, then the conclusion is true. We call this premises. After then, we called it the conclusion. Okay, so this is the mathematical proof. So how to use the mathematical proof? The mathematical proof, when we have premises Q1, Q2 until Qk, implies the conclusion Q. We show it as a tautology, then we can mathematically prove this statement. Okay, just a few seconds. Okay. So to do this, we can use logical equivalence rule, for example, but logical equivalence rule, it's very long, or we can use inference rule. Which inference rule? We already mentioned the inference rule here. So we can use logical equivalence rule from previous week, okay, to prove that this one tautology, but this one could be very long in some cases, or we can prove that this statement, this argument, this one called argument, it's a valid argument using logical inference. What's the meaning of valid argument? Valid argument, it's a logical statement, propositional logic, that have a sequence of a proposition, all of it except the final, all but the final, it's called a proposition or a premission, a, a premises, sorry, and the final called the conclusion. So this is the argument. Valid argument, when this argument always valid, always truth. Okay, so an argument is valid if the truth of its premises all the sequence of statement, all the sequence of proposition given to you implies the conclusion is true. So the truth of this premises, all of it, you can consider is true. Use a logical inference rule to get the conclusion as true, then it's a valid argument. Then this means all this statement is valid. So to prove any argument, any statement is true, you need to use the premises, consider the premises true, and get the conclusion. If you get the conclusion from this premises, then this argument is valid. I will give examples. Okay, first example. We have this premises and this is the conclusion. We can prove that this argument means contain premises and conclusion is valid. How to prove that this argument or this statement is valid? We can use the logical inference rule to get the conclusion from the premises. To do it, we cannot use all these statements. So let's write this statement as a proposition like this. How to write it as a proposition? Shortly, okay, look here. It's not sunny. We can consider sunny as P. So not sunny means not P. And it's colder than yesterday. Colder than yesterday, we can consider it Q. So to write this statement, we can write it like this. Not P, not sunny, and colder than yesterday means and Q. Okay, next statement. We will go swimming. Okay, go swimming. We can consider it as a proposition. We will write it as R, for example. We will go swimming only if it's sunny. Okay, it's sunny means P. Only if means R implies P. Okay, so we will go swimming only if it's sunny. So R implies P. Because we have to use P here because sunny, it's mentioned here also. Okay, if we do not go swimming, it's R. We mentioned it here. Yes, you have to use same letter for same statements. Okay, if we do not go swimming, then not R. Then we will take a canoe trip. Take canoe trip, we can use it as S. So if not R, then S. So this implication also, not R implies S. Okay, take the statement D. If we take a canoe trip, we name it S here. So this one S. Then we will be home at sunset. We will be home. Be home at sunset. We can consider it as small t. Okay, so if then, so it's implication. So S implies T. Also, the conclusion, we will be home at sunset. You see, it's same like here. So we have to give it same letter, which is T. So what we have to prove? We have to use this premise to get this conclusion T. If we use all this premise to guess this conclusion T, then this argument is a valid argument. Okay, let's use A, B, C, D and see if we can get T. But let's plan first. Let's plan for our answer first. Okay, we need T. And to get T, we have to get S alone. If we have S alone, we can get it from here. To get it from here, we have to get R from here. And to get R from here, we have to use this one. So it's like this. We have to start from here and go back until we reach T. This is our plan. Now we have to search for the rules to use our plan. I think it's better to copy these rules here. I think I will copy this rule here so we have it. Okay. Okay, come. All this. I will put it here. Then okay. So we don't need anything else. So this is the premises from the previous. Make it smaller. This is the premises from okay, this same premises here. I copied it here to use it. Okay, as you can see here, from first premise, this one, first premise, let me open the screen. Okay. So we just copy this premise from here. Here, we need to get the conclusion, which is T. Yes. From this premise, we need to get the conclusion T. Okay, we will start from the first one. First premise, we can use simplification rule on this one. If you remember simplification rule, it's here. What it says, if we have P and Q, we can get P. Okay, good. So, as I told you, we need here not P to use it to get not R. From not R here, we can get S. From S here with this one, we can get T. So the plan at the beginning, we need not P. Okay. From this one, we can get not P using simplification rule. When we have not P and Q, we can get not P using simplification rule, because this means this is true and this is true. So we can take this one. Okay, so this first step from first premise, it's given to us, this first line. So using simplification rule for statement 1, we can get not P. Look, we already have premise, this one. R implies P. So it's a premise given to us. Premise means some statement given to you. Look, from 2 and 3, we can apply which rule? Empty rule. Empty rule says if we have not P and R implies this both statement and R implies P, okay, not P, P, then we can get not R. So using empty rule on statement 2 and statement 3, we can get not R. Okay, we have premises here. Not R, it's a premises. Statement 5, it's a premises given to you. Not R implies S. Look for both this. Not R and not R implies S. Okay, there is no rule like this. No, there is rule. Actually, ignore not R. Consider it as a Q, for example. Consider this one as a Q, this one as a Q. Which rule? Yes, it's MP rule. When we have Q and the Q implies S, then we can get S. So if we use MP rule on statement 4 and 5, this is statement 4 and 5, so not R implies S, we can get S. So at the statement 6, we get S from statement 4 and 5 using MP rule. Now, we have premises that S implies T. So, statement 7, it's a premises given to you that S implies T. Okay. S and S implies T. Of course, using MP rule on statement 6 and 7, we can get T. And that the proof. We get T, which is the conclusion, using these premises. Okay, one question. Is it necessary to use all the premises? No, not necessary. The most important to get the conclusion. If you get the conclusion from 2 or 3 premises, it's okay. You have some premises extra, it's okay. But we can get the conclusion. Okay? So the most important to get the conclusion from the exist premises. So we get the conclusion. This means it's a valid argument. Okay, another example. Before go to the next example, any question? Do you have any question?
No, sir.
Okay, so let's continue. Oh, Ahmed, you are here. You said no, yes?
Yep, and always on the class, sir.
Okay, okay. You are welcome, Ahmed, here. It's good that you are always in the class because you are not in any game now. You said last time you will convince me to become a gamer like you. Okay, so let's continue. This another example. This example says, suppose that means we give you a set of premises. Prove that, so this premises, this conclusion. So you have a set of premises. Suppose this means consider this statement true, and from this statement get the conclusion. Okay, so it's direct without the English statement here. We give you premises and we said get the conclusion. Now let's make a plan first. How to get this one? Not R implies S. Actually, S, it's here only. Okay. And R here. So from this, we need to get something uh, like containing not R and Q at the same time to use it with this one. A Q, it's here. Okay. So we will connect between this one and this one to get a Q and not R at the same statements. Okay, so let's start from this one and see what we can do with it. Okay, P implies Q. Sometimes it will be difficult a little bit to think, but you need to practice more example to know how to think about these statements. Okay, P implies Q. We can use the logical equivalent rule. Which logical equivalent rule? I mean, from previous lecture, we have a set of logical equivalence rule. P implies Q. It's equivalent to not P or Q. We have rules like this. Yes, here. First one, the one that I said for you is very important to know it. P implies Q. It's logically equivalent to not P or Q. Okay. So from first premise, this premise given to you, we can get not P or Q. Okay, we have another premise here, not P. Why we blend here? Because we need this not P, okay, here. So not P or Q, this from logical equivalence for the first premise. We have second premise, not P implies R. It's a premise. Also, we will use logical equivalence rule. And from this one, we can get P or Q. How to get P or Q? Okay, not P implies R. Same logical equivalence rule here. Use logical equivalence rule. So here R. You can get not first one or second one. So not P or R. This one means P or R. Yes. So from this premise, we use logical equivalent rule on this statement 3. It's a premise given to you here. We can use logical equivalence rule to get P or R. Now, look, we have a statement 2 that we get it. Statement 2 that we get it from the logical equivalent rule, and the statement 4 that we get it from logical equivalence rule. Look to these two statements, not P or Q and P or R. This actually, we can use the resolution rule for it. You remember here the resolution rule? Look to the resolution rule. P or Q, not P. P, not P. And we have or Q or R. Then from this, we can get a Q or R. Okay, we are going another step in our plan here. So from statement 2 or 4, we can apply resolution rule to get this statement. Let me write the statement here. Not P, this is statement 2, or Q, this is statement 2. Statement 4 says what? Here, P or R. Yes? So resolution rule said not P. P, then we have Q or R. So we can get the Q or R. So at fifth statement, applying resolution rule at the second and fourth statement, we can get a Q or R. Okay. Now we will use the logical equivalence rule for this statement 5. We can get R, not R, implies a Q. From where? This one, from logical equivalence rule. A Q or R give us not R or Q, implies a Q. If you cannot know it from where, actually the idea we need not R. We said that we need not R. Yes? But here, not R now, or R related with the Q, so we need it with the Q to use it to get S here. So the idea here, to get not R from this statement, we need to use logical equivalent rule. Okay, if you remember, this is the rule I give to you now. Another time. Actually, we can always use the main rule to get any rule for logical equivalence rule. The rule says R implies Q. It's equivalent to a Q or not R. Also, it's equivalent to not the Q or R, doesn't matter. Because or statement, you can use this one or this one. Okay, but we need this one. Okay, so the opposite, if I have a Q or R, we can get not R implies Q. This is the original, and this we can get it from here. It's the opposite way. So from logical equivalence rule, if we have a Q or R, we can get not R implies a Q. Look to this statement 6 and the premise, this premise, not R implies a Q implies R, a Q with the Q here. So X implies Y, Y implies Z, then X implies Z. Yes? This is the rule of HS here. HS rule. P implies Q, Q implies R, then P implies R. Same idea here. We have statement 6 and the statement 7. If you look to statement 6 and the statement 7, not R, doesn't matter, not R, Mahmoud, Ahmad, table, anything implies a Q, and the Q implies S. These two statements together give us that not R implies S. So applying HS rule for statement 6 and 7, we get that not R implies S. And that's what we need. So we use the premises and we get from this premises what? The conclusion. So this is the conclusion, yes, here. We will take third example, then we can take a break. Okay. Third example, it's not long. It's have a lot of statements, but it's not long. Let's take a look for it. If it's Saturday, okay, this means if today is Saturday, we can consider it as P. Then we play or we will play soccer or basketball. Play soccer, we can consider it as a Q. Play basketball, we can consider it as R. Okay. So P implies a Q or R. This is a statement, first statement. P, which is it's Saturday, implies a Q or R. A Q, which is play soccer, R, which is play basketball. Okay, continue. If the soccer field is occupied, someone playing in the soccer field, it's already occupied. So we can consider this statement as S. We do not play soccer. Play soccer, it's a Q, so it's not a Q here. So S implies not a Q. This the statement here. S implies not a Q. Okay, next statement. It is Saturday. So it is Saturday. And the soccer field is occupied. So it is Saturday. Saturday, it's P, first one, P. Soccer field is occupied. You can see it here. It's S. So it is Saturday. It's a statement alone, correct statements. Another statement, it's better not to connect with and here because already each statement you can use it alone actually because it's give you information. So it is Saturday. You can stop here. Yes. The soccer field is occupied. You can stop here. So there is not necessary to connect using and here. It's just give you information here and information here. So P is a premises, S is a premises. It's a fact given to you. P that it's Saturday. Q, that the soccer field is occupied. Okay, what we need? Prove that we will play basketball. Play basketball. What's play basketball? It's given to you here. It's R. Or volleyball. Play volleyball, which is you not given to you yet. You can consider it. Here they consider it as T. Actually, this example from the book, but I would not like to name this one T because we use T for true, yes. But in the logical inference rules, there is no true or false or something like this. So they use T usually, but we can use anything else. We can use K, for example. K means we will play volleyball. So R or K. K is not given to you before that. It's in the proof. You have to prove that we will play basketball or volleyball. But as you can see here, volleyball, it's not given to you in any premise. But it's okay. What's the idea? The idea, use the premise to get the conclusion. This is the conclusion, this three premises, and this one the conclusion. Okay, let's write the premises. So the premises P give us Q or R, S give us not the Q, and we have P also alone as a premise. We have S as a premise. We need to prove that R or K. I named volleyball as K, not T, because I would not like to confuse you between T as a premise, as a proposition here, or T as true, because we usually use it as true, okay? Especially T capital. Okay, let's go to the proof. So from this, we have to get this conclusion from this statements. If you look to this statement, actually, we don't have K in the premises. So we don't care about K because using OR, we can connect with anything. So the most important, we have to get R. To get R, it's here only, yes? But to get R, we have to remove this Q and we have to remove this P. Okay, we have P here, we can remove it. Q, it's here. So we have to use this S with this one. I'm doing like a plan to how to answer it. So we will start with this one. Okay, so this is the premises, and this what we need to K. We need to prove this R or K. Okay, this premises given to you, and this premises P given to you. From statement 1 and statement 2, you know this one. You can get this one using MP rule. If you remember MP rule, P with P implies a Q, it's give us a Q. So consider this one anything. So we have P with P, then we can get, we have P with P, then we can get this part using MP rule. So using MP rule, apply MP rule for statement 1 and statement 2, which is given to you here. We can get what? A Q or R. Okay, we have now Q or R alone. Good. I said we need R. So we get first Q or R alone. We have this one. S implies not Q. S implies not Q. We need only not Q alone. To get not Q alone, we can use S with S. So it's given to you premises, fourth statement. It's a premises given to you here. Oh, what I did? I moved here. Okay. This premises given to you here. S implies not Q. And this premise give you here, which is S. So S with S, we can get not the Q using also Ampere rule. So we use Ampere rule in statement 4 and 5. But Ampere rule do not have not. Doesn't matter what you have in this place. Not the Q, and R, Q or R, Q and Muhammad, Q and Ali, anything. The most important that we have S implies anything with S. So we can take S with S together, then we get this one. Okay, not a Q. So from this two, we get not the Q. Using what? Using also Ampere rule. Okay, look here. We have not the Q here. Okay. And we have this statement here. From we take this statement from 1, 2, we get 3, yes? From 4, 5, we get 6. Now we need to connect the 3 with 6. As you can see, let me write 3 and 6. 3 says Q or R. Okay, 6 said not Q. You remember this rule? We have not Q, we have Q or R. It's the DS rule. Here, DS rule, you can, I will show you. DS rule said if we have P or Q and we have not P together, we can get Q. So same idea here. We have what? We have not the Q and we have Q or R. Take this together, you can get R. So applying DS rule here in this statement, applying DS rule on statement 3 and the statement 6, we can get R. Okay, get R. But we need R or K. Okay, we can get R or K. We said if you have any premise, you can use or with any other premise. If you have this one true, you can make or with anything because you have this side true already. Then put anything here, the statement is still true. So we can use the addition rule on this statement R. We can set R or anything, or K or T or R or Z or Y, because we proved in statement 7 that R is true. So R or K also is true using addition rule. So it's correct. That's how we can improve this statement. You can see at your book, in the book, page 78 exercises from 3 to 8. You can solve this exercises from 3 to 8 to make more practice. Let's take around 10 minutes break because we will take another uh, another subject related to same subject. Okay, so see you after 10 minutes. Okay, assalamu alaikum again.
Alaikum salam.
How many one around? Raise your hand, please. Raise your hands.
Okay.
Okay. Okay, let's continue. Okay, what we talk until now today, it's called logical inference. Logical inference. Okay, so logical inference rule, it's actually give you a formal proof. But in mathematics, usually we need a lot of proofs. If we use always the formal proof, okay, we need the statements, and every statements you have to mention which logical inference rule, which logical equivalence rule, and so on. It will be too long, especially with some mathematical statements. So in this case, we can use, instead of logical inference rule, which is a formal mathematical proof, we can use the mathematical proof. Mathematical proof, it's considered informal comparing with logical inference. It's still some formal ways, a mathematical proof, but it's not restrict. We mean here it's not restrict too much as the logical inference rule. So uh, it's give you faster way to make the proof. The mathematical proof give you faster way than the logical inference rule. What the mathematical proof contain? We can apply more than one rule in one step, not only one rule. You can apply more than one rule in one step. You can skip some steps if it's known. You can use some axioms. Axioms means something that it's true. Everyone know it's true. For example, sun come from the east. It's true. Everyone know it's true. There is no need for proof this statement. So this is the mean of axioms. Okay, you can use axioms, things that everyone know it's true, so you don't need to prove it. So you can use it. You can um, use the inference rule, also any rule. With some inference rule, even you don't need really to state it. But of course, you have to use it as a formal way. We have ways for mathematical proof. Okay, we will take examples. Let's first speak about terminology. So in mathematical proof, you will find terminologies like theorem, conjecture, axiom. Okay, what's the theorem? Theorem, it's a statement that can be shown as true, like a proposition given to you. We give you propositions, so you can consider it as a true. Uh, Lemma means some theorem that can be used to prove as our theorem. If we have X, then we can get Y. Doesn't matter to know these names, okay? Too much proposition, lemma. We already take proposition. And corollary, okay? Corollary, it's theorem that follow another theorem. It's come from another theorem. So shortly, theorem, it's a statement that can be shown as true. It's always, not always, it's almost given to you. Conjecture, it's a statement that it's proposed to be true, but not being proved. We have to prove it. Okay, axiom, it's a statement that assumed to be true. This means it's statements that do not need to prove. Like I already give you example that, okay, the sea is salty. Everyone know it. The sun come from the east. Okay, everyone know it, and so on. Okay, we have many types of or many methods of mathematical proof. We will take these methods and we will take examples for these methods, like direct proof by contraposition. You remember the contraposition when we said if we give you P implies Q, you can write it as not Q implies not P, not P. This is a contraposition. We can prove using this contraposition, okay? A proof by contradiction, we will mention it. We start with the opposite of the conclusion to get something, have contradiction, have something that impossible to happen. So if it's impossible to happen, then the opposite of our assumption not correct, this means our assumption is correct. The idea like this. We will take examples. Proof by cases. If the statements have specific cases, we can take each case and prove the case is correct. So the whole statement will be correct. Okay, let's take one by one. Direct proof. Direct proof, it's actually to prove that P, if we have premises, then we can reach the conclusion. Premises, this one could be many statements, not only one statement, give us the conclusion. This is the direct proof. Let's take example. So, first method for the mathematical proof, it's direct proof. It's proving that P implies a Q. So we start with P, the premises, maybe more than one premises, and we get the Q. So this is a direct proof. So far, all the proofs in the logical inference that we take, it's a direct proof actually. We start from premises and we get the conclusion. But here's a different in mathematical proof. We can use any axiom. We can use any proof theorem that we proved a theorem before that, then we can take it as a theorem. We can use inference rule, we can use logical rule. It's give us more choices. Okay, look to this example. In this example says, it proves that if n is an odd integer, so this P, n is an odd integer, then n to power 2 is also odd integer, so this is q. We need to start from p and get to q. Okay, so this is the way. We have n as odd. This is the assumption, and we use this assumption to reach that n to power 2 is odd. This is our goal, to reach from the assumption this goal. Okay, let's start from the assumption. It's given to you n is an odd. So if n is an odd integer, then we can write n as 2k plus 1. Okay, if there is exists integer k and n it's odd, then n equal 2k plus 1. This actually the general form for any odd. So any odd integer, it's 2 multiplied by integer plus 1. For example, we have 1, it's odd integer. So it's 2 multiplied by 0 plus 1. 2 multiplied by 0, it's 0 plus 1, it's 1. We can get any odd integer from this one. Okay, consider k as 1. So 2 multiplied by 1 plus 1. It gives us 3. So this first odd integer, the second odd integer. 2 multiplied by 2 plus 1, it gives us 5, and so on. So the general form for any odd integer can be written like this. If n is an odd integer, then we can write n, and we have k as any integer, exist integer, then n equal 2k plus 1. Plus 1, this makes the integer odd. Yes? Okay. So we need now to get that n to power 2 is odd. How to prove it? If n is odd, then n equal 2k plus 1. Now we will make it to power 2. Instead of n now, we write, instead of n, we write 2k plus 1. So n to power 2 equal 2k plus 1 to power 2. You know this one, this equation? It's perfect square, yes? Perfect square. How to calculate the perfect square? It's the power of first side, the power of second side, plus first side multiplied by second side multiplied by 2. Or you can calculate it like this. 2k plus 1 multiplied by 2k plus 1. Yes, you can calculate it like this if you don't know the perfect square, but you have to know the perfect square. So it's this one become 4k to power 2. This one become 1 as it. And 1 multiplied by 2k multiplied by 2. It's become 4k. Okay, now we have plus 1. We need to get the plus 1, this one alone, a plus something multiplied by 2. something multiplied by 2 plus 1 means odd. Yes? So we need to just rearrange this 2k, okay, 4k to power 2 plus 4k. All this, I don't like the writing here in the computer. All this plus 1. We just make this one here. Okay. And it's equal. Here we can take 2 outside. Yes. 2 from this one, 2 from this one. So it's 2. What is still inside? 2k to power 2 plus. And we take 2 from this one outside here. So it's 2k. All this plus 1. So it's the general form for what? For the odd. Something here multiplied by 2, any integer value multiplied by 2 plus 1, it's odd. Yes? So because k is integer, then this one inside 2k to power 2 plus 2k, it's also an integer. So 2 multiplied by integer value, it's even. Even a plus 1, any even value plus 1, it become odd. Then 2 to power n to power 2, it's odd integer. Why? Because we can write it as, when we start from this one, we get this one as here 2 multiplied by 2k to power 2 plus 2k plus 1. So even plus 1, it's become odd. So we proved that n to power 2, it's also odd integer. If n odd integer, then n to power 2, it's also odd integer. This direct mathematical proof. As you can see, it's a short proof, but with my description, it's become long little bit. Let's take another example. Show that if m and n are both square numbers. What's the meaning of square numbers? Numbers that if you get the rules, you will get, if you have number m and you take its root, you will get integer value. This is the meaning of a square number. You will get value without a fraction, this means. And this means that m, it's actually equivalent to some number u or something like this to power 2. So when we make a square for it or root for it, we can get integer value u. Okay, so this is the meaning of m is a square number. Square numbers, this mean when we take its root, we get integer value, value without any fraction, without any dot 5, dot 4, no. It's do not have in the result. So this is assumption. Okay, m and b are both square number. Then mn means m multiplied by n is also square. So this the premises, this the conclusion. We need to prove this. So we have to start from this one. Imagine this P. So we have to start from this one P to get a Q. And this one a Q. Okay. Mathematical proof. Direct mathematical proof. If M, we assume that this one is true, then we prove that this one is true from this assumption. Okay. So we assume that M and N, not that chocolate, that is sweet, okay? M and N are both square. If they are both square, then there exists integer number U and V. Integer number means number without a fraction. That's M equal U to power 2, N equal V to power 2. So there exists integer number that its square equal M, because M is a square number. And there exists number V, any number means that its square equal N, because N is a square number. Okay, now we will always this mathematical proof like this. You start from the left side, the given information, and apply this information here. Even in the previous example, as you can see, we suppose that this one is true, then we apply the value of n here with the n to power 2 to get that it's odd. Same idea here. We get the value of m and n and we apply it here. If applying it here give us a square, then we prove this one. Okay, so m multiplied by n. Okay, this is the assumption given to you. Then m multiplied by n equal u to power 2 multiplied by v to power 2. Okay, you know in mathematics, x to power 2 multiplied by y to power 2, it's equal to x multiplied by y all to power 2. Yes, so u to power 2 multiplied by v to power 2, it's equal uv to power 2. This one integer. So integer to power 2 means m and n is m multiplied by n is a square also. And that's what we need to prove. You can solve this exercise at home. It proves that if n is an even integer, we proved here for the odd, okay? You need to prove it for the even in the house. Okay, prove that if n is an even integer, then n to power 2 is an even integer also. Prove it at your home. Okay, let's take the second way for mathematical proof, which is proved by contraposition. Yes, Ahmed, I had last year touchpad, but unfortunately it's broken. So I need to buy a new touchpad. Yes, I try it. I tried it last year with discrete mathematics inside the lecture, and it was very comfortable. I will try to buy a new one, inshallah.
Sir, I guess you just muted yourself, so we cannot hear you.
I forget to open the sound, or I don't know. Maybe I close the mic. Okay. Proof by contraposition. We know that P implies Q. It's logically equivalent to not Q implies not P. So if you prove not Q implies not P, then this means P implies Q. It's correct. In the direct proof, we use this one. Why we should use this one? Why all this turn and go from direct proof we go to contraposition? Actually, in some proofs, it's take long steps and more difficult to prove directly P implies Q. That's why they found the other way. Okay, P implies Q. If we said, if we start from the conclusion and we said that the conclusion is not correct and we reach that the assumption not correct, this means the opposite, which is the assumption implies the conclusion is correct. So this is the idea. Okay, and why we all this turn and we have to go for the contraposition, because I told you sometimes it's easier than the direct proof to prove the contraposition. If you prove the contraposition correct, then the original direct proof correct. So how to use it? We will start with the conclusion, and not with the conclusion, with the opposite of the conclusion. So we will start with not the conclusion. We assume it's correct, and we finish that not the assumption correct. In this case, we said if not Q give us not P, this means P will give us a Q because they are logically equivalent. So this is the idea. The idea here with examples, we have P and we have a Q. We will start from not Q to reach not P. If we reach from not Q, not P, then the proof is correct. Okay, so in this example, what this example says? This example said it proves that if n is an integer and 3n, okay, plus 2 is actually this part, the most important, it's P. 3n plus 2 is odd, then n is odd. Okay, this P implies Q. Now we will start from not Q to reach not P. What not Q? Q, N is odd. Not Q means N is even, the opposite of odd, even. So we will prove it by contraposition. We suppose that N is not odd, means it's even. They give us a Q says N is odd. We start with not the Q. So we start with N is not odd, so it's even. If N even, so there is exists integer K such that we can write N as equal to K. This is a general form for even number. N even number means N equal to K. You can calculate it actually. If K equals 0, then N equals 0. If K equal 1, then N equal 2. If K equal 3 equal 2, then N equal 4. So as you can see, we speak about even numbers. So this is a general form for the even number. N equal 2K, considering K as integer, any integer number. So, okay, now we need to apply this in the left side. So now we need to prove that this one also odd, also even. Sorry, because we speak from not Q, reach not P. Okay, how to use it? The statement 3n plus 2. Now take the value of n from here. So 3 multiplied by value of n, which is 2k plus 2. It's equal 6k plus 2. Okay, 6 and 2, we can take 2 outside, yes? So 6k plus 2, we can take 2 as common number, yes? What is still inside? This divided by 2, this divided by 2. So we have 3k plus, if you divide by 2 and multiply by 2, you did not change anything, yes? So 2 multiplied by 3k plus 1. 2 divided by 2 is 1. Okay. You're watching TV during the lecture and you open the mic. Don't attend the lecture if you want to watch TV. Just watch TV. Okay. So look to this one, 3k plus 1. It's integer value. Integer. Because k is integer, yes? So 2 multiplied by any integer, it's even. Yes? So we reach here that 3n plus 2, it's equal to 2 multiplied by 3k plus 1. 3k plus 1, it's k is integer, so 3k plus 1 is integer. So 2 multiplied by any integer, it's even. Therefore, 3n plus 2 is also an even integer. So we start with not the q, which is n is even, and we reach not b, which is 3n plus 2 is also even. So we prove the contraposition. And in this case, we can say that this statement is true, because if we have the contraposition true, the original statement is true. Okay, another example for contraposition. Contraposition. Okay. Again, when we have assumption, give us conclusion. Contraposition means we start with the opposite of the conclusion to get the opposite of assumption. Okay, let's take a look. See the proof, 2 lines only. Okay, look to the, here's the assumption, here's the conclusion. The assumption said if n equal a multiplied by b, where a and b positive, then a less than or equal n, or b less than or equal n. Okay, so we have to start with the opposite of this one to reach the opposite of this one. This one P, this one Q. So we will start from not Q to reach not P. What is not Q? Not Q means here A less than or equal N. Its opposite A greater than the root of N. And the opposite of this one, P greater than the root of N. This is the opposite for this one. Yes? So assume that both A and B is larger than, because the opposite of A, I give you that A less than or equal the root of N. So what's the opposite? A is greater than the root of N. So we assume the opposite, assume that both A and B are larger than root of N. Then we need to apply it here, apply this assumption, sorry, not this statement. Then we need to apply our assumption here. How to apply it? We have to get A multiplied by B. Then the assumption that A greater than root of N. The other assumption, P greater than root of N. From this, A multiplied by B, A multiplied by B, it's greater than root of N multiplied by root of N, which is N. Root of N multiplied by root of N means N. So A, B is greater than N, depending on this assumption. So from this assumption, then we have A, B greater than N, so that N not equal AB. Look, the opposite for this. We said that N equal AB. We need to get its opposite. We said that AB is greater than N. Okay, 5 is greater than 2. This means 5 not equal 2. AB is greater than N. This means N not equal AB. So from not Q, we reach not B. And that's a proof. A proof by contraposition. This means our original assumption is true. So, since the negative of the conclusion implies the negative of hypothesis, then the original conclusion statement is true. This is the proof of contraposition. Okay, you can try this exercise at home. Home exercise. Prove by contraposition that if n to power 2 is an even integer, then n is even. How to prove it? You will start from n is odd, is not even. Then if you get that n to power 2 is also odd, then the statement is correct. This statement, it's very difficult to prove it with the direct proof. That's why it's better to prove it with the contraposition. Actually, the contraposition of this statement is same proof as what? As this direct proof. It's same proof as this one. If you look, this statement actually, this statement, it's the contraposition for this statement. So if you take the contraposition for this statement, then the proof become very easy. You can use same as this proof here. After take the contraposition. Okay. A proof by contradiction. Actually, the problem some students confuse between contradiction and contraposition. And sometimes in the exam, we said proof by contraposition. They prove by contradiction. Sometimes we said they prove by contradiction. They use contraposition. You have to differentiate. We already take contraposition. Now contradiction shortly, okay. Uh, we will start. We will start with uh, not P. We always think to prove P implies Q. Yes. Now we start with not P. The contraposition, we start with not Q, okay? But contradiction, we start with not P and reach something impossible, like R and not R. R not and not R, it's impossible to be true because anything with its negative, it's false. But we said if we start with not P and we reach that this one is true and this impossible, then our assumption from the beginning not true, then not B not true, then P is true. So this is the meaning of contradiction. Some two things conflict, have contradiction, have something that impossible to happen. So we start from the opposite of our assumption and reach something impossible to happen. This means the opposite of our assumption not correct. If the opposite of our assumption not correct, negative of our assumption not correct, this means our assumption is correct because not give us the positive, the correct. This is the idea of contradiction. Okay. So contradiction, we start with not the assumption and reach the meaning of this something impossible. Okay. And we reach something impossible if we start from not P and we reach something impossible. This means not P not correct. And in this case, P is correct. That's what we need to prove, that P is correct. So this is the meaning of R and not R. R not R, it's impossible to be true. Okay, so this is a different. Contradiction, we start with the opposite of our assumption. Contraposition, we start with the opposite of our conclusion, not our assumption. Okay, this is a different. Okay, here, prove by contradiction, there is no positive integer n such as n to power 3 plus 1 equal 100. Okay, how to prove it? We will start with not P and reach something impossible. If we reach something impossible, then it's true, the original assumption. Okay, let's prove by contradiction. How to start? We start from not P. So not P means n to power 3 plus 1 not equal 100. Okay, so if we will take here some values to make it possible to know it. Let's take all the values of n. N, it's integer, yes? So I will take one integer to make this one. I will take one integer to make this one less than 100, and the next integer to make this one more than 100. This means it's impossible to be 100. How to get that this impossible to be 100? Like this. If we take, for example, n to power n to power 3 plus 1, we can use some numbers. For example, if we said n it's equal, for example, 10. So it's 10 to power 3 plus 1, it's around 1001. Okay, this more than 100, like this. If n integer, yes, it's the numbers. We will take all the numbers, integer number. How to take all the integer number? We will go for any place, for example, 0, 1, 2, 3, 4, 5, minus 1, minus 2. We will go to any integer, and we prove that all the integer value less than this and all the integer value more than this cannot give us 100. How to prove it? We can take 2 and 3. So 2 and 3 give us all the possible values. So if n less than or equal to, and if n more than or equal to 3, this give us all the possible integer value, yes? Okay, we take n as 2 and 3, less than or equal to, more than or equal to 3, and apply this one here in this statement. So I have to remove this one because I don't have a place here. Okay. Then n to power 3, which is 2 to power 3 plus 1 must be more than 100. Yes, but calculate it. Okay, 2 to power 3, it's 4 multiplied by 2, which is 8, plus 1, it's 9. But 9, it's less than 100. So cannot equal actually 100. So this is impossible. And we take a 3. 3 to power 3 plus 1. It must equal also 100, yes? Because we give the rule here. Okay, but this one, it's equal 28, which is also less than 100. So it's also impossible. But someone will say, but if I take another numbers, maybe um, because all the values here less than 100. I need to prove that two numbers, sequence number, like 3 and 4, 4 and 5, 5 and 6, because I will take everything less than it and everything more than it, give us numbers less than and more than 100. The only two numbers that give us this, 4 and 5. So if we take instead of 3 here, if we take this one 4 and this one 5. So n, it's any number less than or equal 4. N, it's any number more than or equal 5. Apply it here, you will get what? You will get r to power 4 to power 3 plus 1, which is 65. If you apply 5, you get 160. Then you will never get a number applied here equal 100. Because when we take this two sequence number, 4 and 5, 4 give us number less than 100, 5 give us number more than 100. And between 4 and 5, there is no integer number. So you cannot get a number for n that n to power 3 plus 1 give you 100. It's impossible. So we reach impossible assumption here. So if it's impossible assumption, there is no. We reach from B, that there is. This is the opposite of there is no. There is no positive integer. So the contradiction here, that we suppose that there is integer number. But when we try all the numbers, there is no number give us number equal 100. So it's impossible to have one number applied here. This means there is no positive integer is true, because the contradiction is impossible to be true. I know maybe you confused little bit here. Let me organize it again for you. What's the idea of contradiction here? The statement said there is no positive integer can be filled here instead of n to give us 100. Okay, I assume not B. If I get contradiction here, if I get impossible value here, this means not B is not correct. So B is correct. Okay, what not B here? B is there is no positive integer. Then not B, there is positive integer. So our assumption not B, that there is positive integer n, such that so we assume the positive, the positive of B, not B. So there is no positive. We assume that there is positive. And we try to get this number. How to get this number? From any integer value. Okay, integer value, we can take it from the number line. Yes, it could be 0, it could be 1, it could be 2, it could be 3. To take all the numbers, you have to take two numbers. Okay, you take anything less than this number, for example, 4, and anything more than it means anything more than 5. There is no integer between 4 and 5, yes? Why I take 4 and 5? Because 4 give me number less than 100. So any number less than 4, of course, will give me number less than 100. Why I take also 5? Because 5 will give me number more than 100 and it's direct after 4. So 4 and 5, any number more than 5 will give me number more than 100. So this means all the number less than 4 give me number less than 100 when we apply this number here. And any number more than 5, when we apply it here to n power 3 plus 1, will give me number more than 100. So it's impossible to get a number equal to 100 from a positive integer. When we apply this positive integer to this statement, n to power 3 plus 1, it's impossible to get 100. Okay, so we start from not B and we reach impossible case. This means B, which is no positive integer, is correct. So we proved the contradiction. Sorry, the lecture finished. We will complete the remaining parts, inshallah, next week. We have a few examples still. You can read the examples and we can take around 20 minutes from the next lecture, inshallah. So, any question before we finish here? Okay, I already gave around 10 minutes extra. I did not watch the time. Okay, anyway, see you inshallah next week. I still have another lecture after maybe 2 hours. So, gole, see you inshallah next week. You can leave the meeting. And I will stop the record here.